a new lecture in nonlinear dynamics. Now, before we start, I have to say that there are lectures on YouTube about this subject that probably are way better than what I'm going to do now. I'm going to put some links on the video. You know, I know at least a couple that are very nice. Some guys. Yeah, but okay, let's start to do the stuff. So before starting, you know, we had this question from last time about why can't we solve these systems? Because we can't. Okay, so I'm gonna just take an example. It's not prepared, it's just an example. Let's do this y, let's say x plus y, x squared plus y, and y dot is, I don't know, minus x plus 3y squared, right? And we just cannot solve them. We don't have any method to solve this kind of stuff, right? And even if you take something like, so on purpose, I'm gonna do this one in this way. So let's say minus y plus 3x squared, okay? So in this case, I guess we could write x2 dots is minus, so we could rewrite this equation something like x2 dots equals minus x dot plus 3x squared or something, okay? So even, you know, x2 dots plus x dot plus 3x squared equals 0, okay? There is no particular recipe to solve such thingies, okay? So this is equivalent to that, okay? There isn't, just there isn't, okay? I don't know how to do it. It's not like we can write. So this is the second derivative of x. I want to emphasize this thing. It's the second derivative of x, and then you have this nonlinearity with x squared. It's not like I can write dx dt is 3x squared t. It's not the same thing. This one, right, we can separate, and then you say, oh, you know, it's t dt, and I'm going to put the integral sign and whatever. Whereas for this guy, there is no such thing. You cannot do that. It's just, you can't. All right. So these systems that are not, so we have systems that are linear. So here I'm going to write here systems. Okay. And we have the linear ones. So the linear ones are the ones that somehow they can be written with a matrix with numbers in it. Okay. So here, something like, or I don't know, I'm going to put 2, 5, 3, 1. Okay. So it's something that looks like x dot equals ax. And these guys don't have to be 2 by 2, can be any dimension. For these ones, yes, there is a recipe. Okay. And surprise, surprise, the recipe involves a lot of linear algebra because it's linear systems, right? Whereas for nonlinear systems, we cannot, first of all, I cannot put them in this format as a matrix, you know, as a matrix. They're just looking like x dot y dot equals some function of x and y and some functions of, you know, g of y down, and that's it, you know, whereas this f and y could be, you know, it's not just, I don't know, 2x plus 5y. It's 2, if, you know, could be 2x squared, right? Plus minus 5y or plus y. And it's just done. It's non linear. It's just the square just blows everything away, right? You know, there is no recipe. So with this being said, you know, is that do not confound something that looks like this with something that looks like this. They're very different objects. Okay, this is a first order separable ODE. This is a second order nonlinear ODE that it becomes a first order nonlinear system. Okay, So it's just, you know, to clarify, to get rid of the fog a bit. Okay. So our object of interest in this course are systems that are non-linear, that are like this. So thus I cannot solve them. I don't have a recipe for them. Okay, so I have to look for something else. So it's either for these guys, either we do numerics, meaning we just pick initial conditions and then we put the machine to do it. And then you get a solution that starts in 1, 0, and the solution that starts in 2, 0, and the solution that starts in -5, 3. And each one goes wherever they want to. And then you have to do tons and tons and tons of, you know, integration of, you know, seeing these curves, how they look like, just to get an idea what is going on overall, right? But that's a lot of computation to do. Or, you know, we can look at other ways, like, you know, so people 100 years, you know, or 200 years, so they didn't have any computers, they could still say something about this. And actually the father of the methods that we're studying today is a guy, and I mentioned to you last time, I think, Henri Poincaré, right? So this guy, a French guy, he lived at the end of the 19th century, like, you know, late 1800s, and is considered a founder of the modern dynamics, right? You know, because he came with other methods to consider, you know, these nonlinear systems. And what we do today is just something very, very, or what we're starting today, very basic, right? But yeah, okay. So this being said, let's start our journey, huh? You know, for the next 2 weeks. So first of all, so here I'm gonna, you know, we always say that it's good to study the simplest non-trivial case, you know. So I'm gonna start directly with linear 2x2 systems, linear and non-linear 2x2 systems. But my point is that with 2 systems, with 2 equations, is sufficient to get an idea what would happen in higher dimensions, like how to kind of attack in higher dimensions the problems, you know, because the methodology is somehow the same, you know. Well, being in higher dimensions, things can be way more complicated, but, you know, it's the start is there. So let's just say not linear, let's just say 2x2, okay, linear and non-linear ODEs, okay? So first thing that we're gonna start with, we're gonna talk here. So let's take an ODE that looks like this. So here X is in the domain in R2, okay? So if you want, I can make it a vector. Maybe I should make it a vector for you. X dot X, X, yeah? So when I write X, I'm thinking about something that has components X and Y. I know you know that I'm using the same letter, but doesn't matter. Okay, you're smart enough to get it, right? Okay, so the first thing, so we're gonna start with some definitions. The first thing we'll define what is an equilibrium. So a solution, so let's call this one. A solution of one is an equilibrium if x of t, or a solution x of t, if x of t is a constant for all t. Okay, so it doesn't move. And the other, so this is an equilibrium solution. A point x naught in D is an equilibrium point. Okay, I want to distinguish between an equilibrium solution and an equilibrium point. Yeah. If x of t equals x naught is an equilibrium. Equilibrium solution. So people interchange these things as they please, but You know, it's one thing to think about a solution is something that doesn't move in time. It's a function, but I also can think, okay, so it's an equilibrium point. It's like that point that, you know, the value stays fixed at that point for all t, right? So in our discussion, we can interchange these things, you know, equilibrium point, equilibrium solution, as long as we know what we're talking about. You just say it's an equilibrium, okay? You don't have to say point or solution. It's just an equilibrium, okay? So the context, in the context should be clear if we refer to a point as a point or as a solution, all right? Okay, so now as a note and as a modus operandi, right? Equilibria, okay, of one are found by doing the right-hand side equals 0, okay? Or by solving, let's just say by solving the right-hand side equals 0. Why? Well, let x naught be such that f in x naught equals 0. Yeah. Then x of t equals x naught has, okay, then x naught, okay, fulfills, or okay, fulfills. Okay, dx dt equals d dt from x naught is 0. So this is the left-hand side. And then we have f in x naught equals 0. This is the right-hand side. So there you go. This implies that left-hand side equals right-hand side of 1 for all t. There you go. And this 0. Right? So there you go. That's it. So that's how we find the equilibria. Okay. Maybe I should put vector over this F2 because it has to have 2 components. So now if I start putting the vector symbol, I better put it everywhere. Okay, and here, and here, and here, and here. I hope these are all. Yeah. Okay, so let's take an example. Okay, so you're gonna like this, right? So this being said, I'm gonna flip the page. Okay. All right. So for example, let's say, x dot is x minus y, y dot is x squared minus 1. What are the equilibria? Equilibria. Okay, well, we have to do right-hand side equals 0. So this is, right, equivalent to x minus y is 0 and x squared minus 1 is 0. So this is equivalent to x equals y, and x will be plus minus 1. So here is the answer, equilibria at x, y equals, or x naught. So we have a couple, right? So let's say x1, y1 is 1 and 0, and x2 and y2 equals minus 1 and 0. Oh, why did I put 0? Because I'm not on, I don't know, x equals y, right? So it's minus 1. Yeah. I think it's straightforward. Yeah. So we just solve for the right-hand side equals 0. So these are equilibrium points. Equilibrium points, right? And the equilibrium solutions are, if we want to distinguish, right? x1 of t, x2 of t, x1 of t, y1 of t equals 1, 1, and x2 of t, y2 of t equals -1 for all t. Okay, that's the difference. So these are points and these are solutions. Good. I don't think that there are any problems with this thing. Now, the next thing that we have to define is what is stability. Okay. So intuitively, what stability is an equilibrium is stable if what starts close stays close. Okay. So if I have an equilibrium point in the phase space, let's say here is x and y. Okay. So I have here x naught, y naught, an equilibrium. All I want to say somehow in symbols or however, if I start close with another point, I might go away, but I'm not going too far. I'm just staying around. Whereas asymptotic stability will be like if I start, so let's say this is another equilibrium, okay? I'm putting E this time, right? If I start close, well, it's even more, I'm going inside this guy, right? So inside, it's actually wrong to say. Remember, these are pictures that should be thought of in 3D. There is a time component that we don't see, right? So actually, when we talk about tending to the equilibrium point, we should keep in mind a picture that looks like this. So let's say here, I'm gonna do a 3D picture. Okay, just to make sure that you guys are with me. So let's say here is X, Y, and T, yeah? And this is that X, E, Y, E. So this is an equilibrium, meaning in time, it doesn't change its position, yeah? So this is how it looks in 3D. So the position of that object doesn't change in time. And now when I'm talking about something that is asymptotically stable, I'm talking, oh, there is a neighborhood in here, or anyhow, you know, if I start around this guy somewhere, so let's see, I have here some other initial condition, I might go with this solution as time passes somehow, I don't know where, but then at some point, I better get asymptotically aligned to this one. I will not touch it, but I will tend to it. That's why we learned about asymptotes in calculus. Yeah, so I might just do flip-flops or whatever, but I won't go for far, right? You know, I'll just, so this thing would be asymptotically, okay, asymptotical stability, let's say. Okay. Whereas if I talk about the other one, so let's say we take here that other equilibrium here, X naught, Y naught, okay? This is again an equilibrium, so I'll do it with pink, okay? In other words, again, it doesn't move from its position, okay? But now when I'm talking about stability, that is not necessarily asymptotic, what I'm talking is I start close, I will not go far, but I'm not tending necessarily to that pinky line, right? So I'll just go around, I don't know, maybe I'll do something like this, okay? This is just stable, okay? So this would be a stable solution, a stable equilibrium, this the, okay. Not you, the pinky is stable. So this is a stable equilibrium, and this is happening for any other, you know, if I start wherever around here, it will happen a kind of the same thing, right? You know, I will not go far away. Whereas for asymptotic stability, if I start with the one, you know, again in this neighborhood, it will kind of do the same, right? It will just flip around, whatever, but then, you know, at some point, it will just lie down on the thingy, right? So in this case, this red equilibrium is asymptotically stable stable equilibrium. Yeah? So this is the part that is kind of a harder to understand. What do we mean by this? And now I'm ready to write a definition. Okay, so we say that x naught, an equilibrium point, okay, or solution, however, again, I'm going to interchange the, okay, is stable if, actually I shouldn't say equilibrium solution, it's nicer, it makes more sense because we're talking about ODE. Solution is stable if, here, I'm going to make the picture because that's how I know it. Okay, so here is x naught, x of t. Okay, let's write it nicely. I shouldn't rush. X of t. Okay. If for any initial condition, let's say xe in, no, we should say like this. If there is a neighborhood of x naught such that any, okay, let's call it u of x naught, such that any solution that starts in u stays around u. Okay, so if this is, okay, this is u, I'll make it bigger, guys. So here is x naught, here is u, and I'm starting in a different point. I'm starting here. Okay, I should do it with green or something. Okay. So here I'm starting with this one in here, that's xi. I'm going to go around, but I'm not going too far. Okay, I'm starting around, I'm just not going away. Okay, I'm not going towards the point either. I'm just staying around. Okay, that's all I'm saying. So in other words, it's like this blue thingy, right? It doesn't go away, the blue curve. It kind of stays around. Okay. Whereas if we take the same thing and we think about an asymptotically stable equilibrium, what will happen? We'll have limit of, I start close, but as t goes to infinity, for any solution that starts near x naught, for any x of t starting in this u, okay, like it's exactly like here. It's a neighborhood that, I start around this guy and I never go away. Not they never go away, sorry. I tend to the, this would be the u. Where is this one? Where this one is? This is the, okay. I don't want to make it more formal. I can write it in terms of neighborhoods, okay? But I just don't want to go there. I just, I want you to remember the picture if you can. The picture is the better. Because, people, when they do this kind of pictures like this one here, right? You have the feeling that the solution will go into the point and will touch the point, but that's never happens, okay? So it's an asymptotical thing. So that's why I would prefer for you to remember this kind of pictures, right? So with the time in them. Yeah. All right, now what would be an unstable? So these are stable equilibria. What would be an unstable one? It's exactly what is not stable. It starts close and it goes completely out there, right? It's just, you know, shoots somewhere else. All right, so this being said, you know, we have a definition, a kinda, right? So the question now is, okay, how do we, can we compute the stability somehow? Can we say if an equilibrium is stable or not, right? And here how people thought about this. So I'll start directly with a, you know, a general system. So here is a system like the one we had there, right? X dot is x minus y, and y dot is, it was x squared minus 1, right? You know, so for example, all right? And then I say let x naught, y naught be an equilibrium. Okay, all right. So that's the one that doesn't move. What can we do to study things that start near an equilibrium? Look, what I know best is Taylor series, because that's what approximations, that's how approximations are done. So what I'm going to say, okay, near this x naught, y naught, we're going to do Taylor series on the f and g. So we have what? We have f of x and y equals fx naught y naught plus df dx, right, in x naught y naught, and then x minus x naught plus df dy in x naught y naught times y minus y naught plus higher order terms, h of t. Okay, so I'm gonna make this one bigger so you can read it. So y minus y naught plus, when I say higher order terms, I'm referring to terms that have as factors stuff like y minus y naught squared and x minus x naught squared that are so small that we're gonna just say, well, they're almost zero. I'm gonna just ignore these guys. Okay, they're tiny. Okay, so in other words, we just take the first, the linear approximation of f. That's what we're doing. That's a linear approximation. And actually, if you think about f of x and y as a surface in space, z is f of x and y. For every x, y, you have a z, you have a height. What we wrote here is the equation of the plane tangent to f of x and y at x naught, y naught. It's a linear thing. Okay. So anyhow, long story short, I'm going to do the same thing with g. Right, dg dx in x naught, y naught, and then plus dg dy in x naught, y naught, and then plus high order terms that I'm going to say, okay, I'm going to just take them to be 0, okay? And then now I remember what are these guys? These are equilibria, right? So this is 0 because this is an equilibrium. That's how they're found, by doing the right-hand side equals 0, right? Right? So that's why it is. And now I'm going to write the leftover, right? So what we are ending up with, we're ending up with x dot equals df dx, right? At x naught, y naught, x minus x naught plus df dy, x naught, y naught, y minus y naught, and then y naught is the g dx. Okay, and you're gonna say, so what? Well, these derivatives are computed at points that we know. So they're actually numbers. Okay, so in other words, what we have here, we have a system that looks like this x dot. Okay, let's write it nicely. x dot y dot equals df dx df dy dg dx, and we'll do it on the example in the second, okay? dg dy, x naught, y is not, okay? Let's write it nicely. Okay, as applied to x minus x0, y minus y0. Okay, almost there. Okay, so now I'm going to do one change of variable and say, okay, instead of x, we can take x minus x naught. Instead of y, y minus y naught. X naught and y naught are numbers. They won't change the derivative. So this, okay, so let's call big X to be little x minus little x naught. So this means that x dot will be little x dot, and that's it, because x naught is a number, okay, is a constant. And then I'm going to take y to be little y minus little y naught if you want. So y dot will be just little y dot. And then in this way, I can write my system something like this, right? So df dx, df dy, dg dx, dg dy, okay, and this applied to x dot and y dot. And what we get here, it's something that is in the linear world. So I know, I'm not sure if you followed me, but I'll do now the example, and that's when people get like, oh, okay, all right. So this is like the theory part. So here is our example. So we had what? We had little x is x minus y, little y x squared minus 1. And let's take the equilibrium at minus 1, okay? Just to make it different.
Sorry, isn't the right side at the top supposed to be just x and y?
So what do we have to do? Okay, so once again, this is x equals, what right up on the top? I'm not
the
following.
matrix form. The x, y, you have it as x dot y dot on the right side there.
Yeah. Oh,
just
with,
x and y?
no dots, no dots. That's absolutely correct. Thank you. Okay, good. Yep. Good. Someone is following me. Good. All right. So what do we have to do? So this guy is F, this guy is G, yeah? So now I'm going to write directly that system with the capital letters. So this becomes the following. So I have to take the derivative with respect to f of the function that is up, right? So this will be 1. And then the derivative with respect to y, this is a minus 1. And then the derivative with respect to x, so this would be a 2x here, but then I have to compute it in x naught is minus 1 and y naught is minus 1, yeah? I'll just write it like this. And then the derivative with respect to y is 0 in this case, yeah? And then apply to xy. So what do we get? We get x dot y dot equals 1 minus 1 minus 2, 0, applied to xy. Okay. So this near this equilibrium, which in this case is -1, 1, or in the theory world would be an x naught, y naught, we can approximate the ODE that is given, that system, with something that is linear, okay, with a linear system. So we end up with something that looks like x dot equals ax. But this is true only near, in this case, -1, 1, okay? Near there, okay. But this is sufficient for us, you know, to study what is happening near there, because when we talk about stability, we say, oh, we have an equilibrium. So if we start near an equilibrium, if we stay around, then it's stable. We start near an equilibrium, but near an equilibrium, the system can be approximated by these linear systems, right? So now, as I was mentioning at the beginning, for linear systems, we do have a way to solve them. We have a recipe, right? Algorithmic way to solve them. So if we can do that with the linear system, then we know what is happening near the equilibrium of the nonlinear one, yeah? Okay, so that's the philosophy. So once again, we have something that looks ugly, but we want to study the stability near an equilibrium that we just computed. How do we do this? We just approximate the right-hand side with their linear approximation. So when we do this, we obtain a linear system. We obtain a linear system, we do the stability for the equilibrium of this linear system, which actually corresponds to the equilibrium in our original one. How come? Well, here, right? So remember this, the equilibrium here, right? We do the right-hand side equals 0. Obviously, this would be just 0, 0. So it would be the vector 0 if you want, okay? I'm making it 0, right? It's the vector 0, right? Okay, but the vector 0 here, 0, 0, right? Is nothing else. This is 0, this is 0. In other words, little x is x naught and little y is y naught, right? So the equilibrium in the 0, 0 in the linear system corresponds to our equilibrium x naught, y naught in the original system, right? Because we just did that shift. All what we did there was a little shift to move our origin in x naught, y naught. And now, if we have the equilibrium for the nonlinear system at 0, 0, we can just, if we would know how to study stability of these guys here, then whatever we're getting here gets translated into the stability of the equilibrium of the original system. So now what we have to start doing is to study the stability of linear systems. Okay? Because that one is giving you the answer to the stability of an equilibrium in a nonlinear system, at least for this kind of, there are more kinds of stability, but anyhow, we'll just do this one for now, okay? All right, so the algorithm is the following up to here. You have to compute equilibria, and then you have to compute the linearization of the system around that equilibria via doing these partial derivatives and then writing it as a linear system. And now comes part 2. What do we do next? Well, next we have to know how to study these guys, right? And that's where it comes, you know, the ODE course, right? So stability of 2x2 linear ODEs. Okay. All right. So here comes the the linear algebra that some of you did with me last year. Okay. So here I'm going to write this guy here, x dot y dot equals, let's say we have entries A, B, C, D, x, y, okay, which we write in this way. Yeah, so it's obvious who's who and what is what, right? So A is that matrix on top, right? All right, and now we have x0, y0. Okay, I should be consistent in my notation, right? So x naught, y naught equals 0, 0 is an equilibrium. Just because we have it. We won't need this actually, but anyhow. All right. So now from linear algebra, okay, we can calculate the eigenvalues of A. Remember that, let's calculate the eigenvalues. And let's denote V lambda 1 and V lambda 2 to be the eigenvectors. Okay, and why we're interested in eigenvalues, eigenvectors, is because if we denote by P the matrix that has these vectors as columns, okay, then, so this is the matrix with the vectors V lambda 1, V lambda 2 as columns, okay. Then from linear algebra, we know the following. So here I'm going to write P here again, V lambda 1, V lambda 2, okay. So then if yeah, okay, I should have started with that. If, all right, so then P minus 1 exists, okay, so I should say this here. If P minus 1 exists, then, now actually note if this, the theory tells us that it exists, P minus 1 exists. And we have the following. P minus 1 AP equals the diagonal of lambda 1 and the matrix with lambda 1 and lambda 2 on the diagonal if lambda 1 and lambda 2 are real and distinct. Yeah. Or P minus 1 AP equals lambda lambda if lambda 1 equals lambda 2 if they're equal. Okay. And V lambda 1 is not the same with V lambda 2. So it has distinct eigenvectors, but then it may be that it has the same eigenvectors, and then it becomes something that looks like this. Okay, and finally, it gets to produce something in this way if lambda 1, 2 are complex. Yeah. So they have a non-zero imaginary part. In other words, what we're doing here, we're diagonalizing A. That's what it's called, to diagonalize a matrix. And whoever did linear algebra did this. Was unclear why you did it. And here comes the reason, right? Because you're going to use it right now in this ODEs, or if not today, next time, right? Before we move on. So that's why I was hesitating with P minus 1. Here, given a matrix, okay, that is square. Okay, so maybe I should put M. When does it exist M minus 1? So by m minus 1, understanding that matrix that is the inverse, right? Anyone knows? You can put it in chat if you don't want to say it. When there is an inverse of a matrix, guys, what is the condition for a matrix to have an inverse?
Non-zero determinant.
Oh, yes. Okay. Answer. I'm always. Yeah. Okay. Just to remember this stuff. Okay. All right. So P minus 1 exists no matter what lambdas we have there, by the way. Okay. So that's what the theory says in linear algebra, right? But I kept wanting to ask you, so that's why I was coming back and forth. All right. So why are we interested in this stuff here? It's because what I want to do is to bring this system to a form that is diagonal. And why do I want it on a diagonal form? Because here, I'm going to put it in here. Let's say we have a system that looks like this. X dot y dot equals diagonal, yeah? 2, 0, 0, 3, xy. Oh, in other words, x dot is 2x, y dot is 3. Do you see what I did? I just dismantled it. I just decoupled it. So as soon as it's in a diagonal form, the matrix A, we can decouple the system. And then we can solve these ones, right? So these ones indeed are solvable. So the first one is dx dt is 2x. And the other one is whatever, with y, I won't write it. So this is like dx over x is 2 dt. So these ones indeed we can solve. So you're going to end up with x of t is e at 2t and then some x in 0 or, some initial value there. Okay, a constant. People sometimes write it like this. So here, c1 e at 2t. Okay. All right. So this is the value of this uncoupling of the system. Once you uncouple it, once these unknowns separate each other, you can solve them separately, right? And then you just solve the system in this way. Right? And here, that's why in linear algebra we're so interested in this process of how to bring a matrix A to its diagonal form, because you end up using it in ODEs, for instance, by uncoupling the systems. Do you know what I mean? So here, okay. For now, all we know is that if we have a matrix A, there is a process where we can compute the eigenvalues and eigenvectors, right? And then this, taking P as the matrix with the eigenvectors as columns, then we do P minus 1 AP, we get these diagonal thingies. But this doesn't mean that this system x dot ax is in by any way diagonal right now. So we have to do a change of variables in order to make it, or anyhow, to produce a diagonal system that is related to the original one, and then solve the diagonal one and bring it back to the non-diagonal one, right? So there are quite a few steps going on, right? Okay, so let's see. So for the next step, what we're gonna do, I'm gonna take my fellow here, okay? And I'm gonna propose a change of variables. I'm gonna bring that thing, right? To be y equals p minus 1x, okay? Where p is your friend, right? The one that I just talked about on the other page. So I'm doing this change of variables. So in other words, right? So here we had x of t is what, right? So now I'm going to y of t is p minus 1, which is a matrix with constant entries, x of t, right? So there you go. Shouldn't do that. Okay. So that's what we're doing. So now we had our equation x dot equals ax, okay? So instead of x, I'm going to put what I see there. So, okay, so here this means that x of t is p y of t, yeah? So now instead of x, I'm going to write that thing, right? So x dot, yeah, I'm going to do it like this. Okay, so here with x becomes py, yeah? Okay, so the left-hand side becomes py dot, right, equals, p is constant, right? So this is a constant matrix, right? There's no functions inside, it's just numbers, okay? So there's the left-hand side equals a, and instead of x, p y of t, yeah? Or y, I don't have to put t. Huh? In other words, y dot equals, so here we multiply by p, multiply by p minus 1 on the left. I hope you remember, especially those of you who did the linear algebra with me, that matrix multiplication is not commutative, right? So you cannot do AB is not BA, right? I remember I even put it on the board at some point. Okay, I remember. I don't know about you, but I do, huh? And how many times did I teach this course in my life? Okay, so here, P minus 1, A, P, Y. Oh, but this was the diagonal, right? It was that one with lambda 1, lambda 2, or anyhow, or lambda 0, 0, lambda, whatever, right? All those variants, right? So let's just call this one D, right? And understand that this is the diagonalization of A, okay? So I'm going to put here dot, 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 see the previous page, because that's why I did this thing here. Yeah? Okay. So we end up with y dot equals dy. And now what we have to do is to discuss the solution of this kind of linear ODEs, where D can be something that looks like lambda 1, lambda 2, or D can be something that looks like lambda 0, 0, lambda, or D can be something that looks like lambda 1, 0, lambda, or, so there are 4 variants here, right? It was alpha, beta, and we got here. So in this case, A is 2, 1, 1, 2, yeah? And then we do the eigenvalues, right? So what do? We have to solve determinant of A minus lambda identity 2 by 2 equals 0. So in this case will be the determinant of something that looks like this. Right, so this is the determinant equals 0. In other words, 2 minus lambda squared minus 1 equals 0. Everybody loves this, right? The thing is that I will let you at your test to use Maple or whatever, so you don't even have to know this. Right? Okay, so we solve this however you want to solve it, and you end up with lambda 1 is 3 and lambda 2 is 1. And then we have to do v lambda 1 is 3, right? So v3 and v lambda 2 is 1. Okay, so however you want to call them, you know, so usually we just have to do a minus 3i2 v lambda 1 is 3 is 0, and then you solve for v, and then you end up actually with a vector, okay, for each one, right? So however you want to do it, again, I advise you to review this thing, okay? And then for this one, a minus 1 times I2 v lambda 2 is 1 is 0. So again, okay, we're going to find this guy to be 1, 1. Okay. So P, that matrix, is minus 1, 1, and 1, and 1. Okay, I think that's, I'll just solve this now and stop here today. So now we're going to end up, when we do this job P minus 1 AP and you multiply the three things, what you're going to end up with, if you did it right, okay, this really has to look like the diagonal of the, so this is the diagonalization of A. Okay. So that's linear algebra, like the linear algebra from the course. All right, so we did this job. So now what we're going to do, we're going to write the system in Y. So the system in the Y variable looks like this. Yeah. So let's call the Y unknowns U and V, okay? So basically we have U dot V dot equals 3001 UV, okay? So we end up with U dot is 3U and V dot is V, okay? So we end up with U of T is C1 E at 3T, and V of T is C2 E at T, where C1 and C2 are constants. They're the initial conditions, if you want, yeah? Okay. And now what we have to do, so we got these guys, we have to go back to X, right? So X was, where is it? Py, right? Oops, sorry. Hey. Right, was Py. So in this case, right, where is the P matrix? Minus 1, 1, 1, 1. And then apply to Y, so it's basically this C1 E at 3T, C2 E at T. Or if you want, we can write X equals, maybe this is even better because maybe you'll link it to something that you actually did. Okay. Okay, E at 3. So we can write it in this way. Okay, C1, C2. Okay. So we can write this. So this fellow, this one is this one, yeah? And this guy is this matrix, so this is a row and this is a column, yeah? But if you put it together, that's what you get. Okay, so the thing is that if we're writing in this way, we end up with x of t, y of t, and you'll see why I did it this way. We can read it as C1 V lambda 1 E at 3t plus C2 E lambda 2, V lambda 2 E at t. And this is the form you have been taught in linear, in the second ODE course, if you did it. And even in the first ODE course, I think it sometimes is covered, this stuff. And that's why I put it in this form. The point is that, okay, no matter how you write it, if you recognize it or not, so this is x, right? The point is the following, that from the uncoupled version of the linear system, we can always go back to the x, just multiplying by p in front if you want, okay? All right. Okay, so if we look at dimensions here, this is a 2 by 2. This is 1 by 2 and 2 by 1. That's not good then, right? We have to put it backwards. I think I'm wrong here, right? So let's just put it as it was. I'll feel better about it. There you go. Maybe in this way, right? I think now is better, actually. There you go. Okay, so there's that. All right. And with this being said, now the question is, what do we do with this stuff? Okay, so we have to go back to the stability part, right? So for the stability part, we have to take every case. Okay, so I won't really take every case. I take some cases and discuss and then send you directly to the source. Okay, so you see there what is going on. So again, coming back to the main purpose, right? So we have x, f of xy, y, g of xy, right? And then we have, from here, we have x naught, y naught equilibrium. And then from here, we get to x equals ax, the linearization, okay? And now the linearization, we'll just discuss directly the stability without going through y, but the way it was thought is like we have to uncouple it, and that's what is going on. Okay, so from here, let's say we have 1. Calculate the eigenvalues of A, okay? And there, let's say lambda 1 and lambda 2 are real and they're distinct, okay? And then we have case A, let's say that they're both positive, okay? In this case, basically what we have the system in Y would be a positive and the positive 0, 0, right? So let's say UV. So U dot V dot is, so I'm going to put it like 3002 UV. Okay, so I'm just taking an example. All right. So in other words, here we have that the solutions are U is like E at 3t and V is like E at 2t. I'm just showing you how I'm thinking about it. Okay. Well, this means that these guys are going to infinity, right? ST is going to infinity, right? Okay. So U of t is, actually, we know what it is, right? So it's C1e at 3t. So as t is going to infinity, this guy will go to plus or minus infinity, right? And v of t, C2e at 2t. So as t is going to infinity, this is going to plus or minus infinity. In other words, if I want to do a picture in 3D, right, this is the t, this is the equilibrium, right? If I start here, what is going on, I'll just diverge, I'll just go whoop. If I start here, I'll go whoop, and the other way is whoop, right? The other way, I don't know what it is. I don't do minus infinity, right? Actually, I know what it is. If I start here, I go whoop. So now my question for you is, what kind of equilibrium is this one? Stable or unstable?
Unstable.
Yes, thank you. Okay, and if I do a picture in the phase space, what I will see back in the XY coordinates, this is that X naught, Y naught. And what I will see just stuff going out in all directions. And this is called a source. Okay. It is a source. We cannot have a stable source, right? So it's an unstable equilibrium and it's called a source. Okay, I'll do one more and I'll let you go, okay? So let's say two, that we have the eigenvalues, they're both real, distinct, but they're both negative. Okay. In this case, you would get, you know, something like u dot v dot. You would have something like minus 2, 0, 0, minus 3 uv. Okay. So that u of t would be something like C1e at minus 2t. And v of t would be C2e at minus 3t, which are both, as t goes to infinity, are going to 0. So if I am to do a picture in 3D in the UV world, so this is UV, and that's the 0 solution in the UV world. Whenever I'm starting around, I'll just go and lie down on this guy, right? So the distance, it will just go towards 0, right? Now I'm asking you what kind of equilibrium in this is this one, right? So if I do it in 3D in the XY world, so this is X, this is Y, this is T. And let's say we start here, this is that equilibrium. Okay, it's just a vertical line. It doesn't move from here. And then what we get, we start close. I'm not sure what I'm gonna do, but for sure I'm gonna lie down on this guy, right? Here, if I start here, I might just do, I don't know, a flip or something, but then I end up going like this. Okay, so what I will see in the phase plane, if this is the X naught, Y naught, I will see all trajectories going in. So now question for you so I can let you go. What kind of equilibrium is this one? It's a sink, yes. And it's stable or unstable? It's stable or unstable? Does it fly away when it starts close, or it gets closer to that equilibrium? So this is a stable equilibrium. So let's write it nicely. And it's even better. It's asymptotically stable equilibrium, right? It's an asymptotically stable equilibrium, and it is called a sink, right? As this guy, it is called the source, right? Its name. Some people use other names like stable node or unstable node. The meaning is the same.